All right, so we just explored whether we could decide if we had a function by looking at ordered pairs, tables, graphs, and even equations. So whether we have a function or not, we can talk about the domain and the range for any relation. So just as kind of a quick reminder, I think we've actually seen this back in chapter P when we were looking at some of our rational functions. When we talk about domain, people like to think about domain as the set of first coordinates, or the x values. And when I think of the x values, I think about the acceptable x values. So when we looked at rational functions, we said we couldn't divide by 0, and we looked at places where we would divide by 0. With square roots, whenever we talk about taking the square root of a number, we want to try and get a real number, so that's places where the domain would come in. The range, on the other hand, is the set of all second coordinates, which most of us think about as the y values. So, what I thought we would do is we'd try to decide, do we have a function? So find the domain and range for the following relations. And again, as we look at these, I want you to think about if they are in fact functions. So here's the first one. It's the set of ordered pairs, -1, 7, 8, 26, and 11, -23. Okay, so if we want to find the domain, it's the set of all the x values or all the first coordinates. So here, notice we don't have an interval, so we're going to use set notation and just list them out. -1, 8, 11. When we talk about the range, we're talking about all of the second coordinates, which in this case refers to the y values. So we've got 7, 26, and -23. Okay, and one thing that we should be aware of with the domain and range, if for some reason we had y values repeating, we'd only list it once. I don't care if you list them out in numerical order from smallest to largest, or if you just kind of list them. That's sort of a preference, and I will let you pick how you want to do that. Is it a function? So, if we decide it's a function, what do we have to check? Well, we're looking to make sure that none of these x values repeat. And here they're all unique, so it should be a function. Okay, that was our first example. Hopefully that didn't seem too bad. What I'd like to do now is look at another example, and so we're going to look at a specific equation. So I'd like for us to consider the second example, which is y is equal to the square root of x plus 3. So we know from simplifying square roots that we can take the square root of 0. That was something that was okay to do. If the square root was a positive number, that was totally okay. But we said that if we had the square root of a negative number, do you guys remember that we got an imaginary number? This isn't a real number. So that's a potential problem. So one of the things that we need to do is we're going to look at when the radicand, in this case x plus 3, if it's bigger than or equal to 0. If it's equal to 0, the square root of 0 is 0. If it's positive, the square root of a positive number is something we can find. And then we're going to solve. So we would subtract 3 from each side, and we'd get x is greater than or equal to -3. We could graph that on a number line. We could also write it in interval notation. We'd go from -3 to infinity, and we'd get to include -3. We can look at more examples of these in class if they're still confusing. Okay, with functions we can also talk about a specific notation that's used. So one thing that we'll see with function notation is we typically see something like f of x. Again, this is read f of x. So f refers to the name of the function. It's not always f, it could be g, it could be q, it could really be any letter we chose. And then this x right here is an input value, or our variable. F of x. It does not mean f times x. It's f evaluated at x. So if we want to look at some specific examples, we could consider the function f of x is equal to x minus 3. F of x is really just a fancy way to think about it as y. Okay, and the reason we like function notation is that we can evaluate, if we would have had y is equal to x minus 3, we could evaluate x at different values. That is, we could plug in specific values for x. Function notation makes it a little bit nicer to kind of keep track of what we've evaluated. So I would like us to find f of 4. And the idea here is if we're going to evaluate our function, it's saying that we are going to take 4 and plug it in as our input. So what does f do to any input? It takes the input and subtracts 3. So in this case, we're going to plug in 4 for x and then subtract off 3. F of 4 should be equal to 4 minus 3, or 1. Okay, so you can think of f of 4 as the y value when x is 4, and that's equal to 1. We can also use function notation to try and look at other pieces. So if we consider still f of x is equal to x minus 3, I'd like for us to find a specific value of x given a y value. Okay, so again, we are still looking at f of x equals x minus 3. I would like us to find x if f of x equals 9. So what this is really saying, f of x, remember that's if y. F of x is like y, so that's like saying if y equals 9. So here we're going to think about 9 is equal to x minus 3. And we can easily solve this for x by adding 3 to each side. And we'd get the x value would have to be 12. Okay, if we want to find the y value is equal to 9, we plug in 9 for f of x, and then we solve for x. We get x equals 12 in this case. The last example I want to do with this is I want it to be a little crazier. I want us to think about what is f of a plus 2. Now some of you might panic, but again, remember this is just saying here's an input. What does f do to any input? It takes the input and subtracts 3. So here, if we take the input, that's our a plus 2, and then we subtract 3. I can drop my parentheses. And then we need to think about what is 2 minus 3. So it's really equal to a, minus 1. Looks a little crazier. Again, it's helpful to think of it as an input. So sometimes something I'll do is I'll put my input in a box. And we could think of whatever's in the box. What does f do to box? It takes the box and then subtracts 3. That's something that can be helpful to think about. I would like you guys to take a moment and find a couple other things. So I'd like for you to consider g of x, which is equal to x squared minus 4. And I'd like you to try to find g of 3. I'd also like you to find g of 0. And then I'd like for you to find g of x plus h. Go ahead, take a couple minutes to try this. Okay, you had a couple minutes, hopefully, to pause the video and think about this. To find g of 3. G of 3. Okay, g of x. We plug in a 3 anywhere we see an x. So we have 3 squared minus 4, or 9 minus 4, which is equal to 5. G of 3 equals 5. It tells us an ordered pair if you look at it, which is why function notation can be nice. It tells us we've got the ordered pair 3, 5. G of 0. We take 0, we square it, we subtract off 4, we get negative 4. When x is 0, our y value is negative 4. G of x plus h, this one's a little trickier. So again, we're going to plug in x plus h anywhere we saw an x. So we've got x plus h quantity squared, and then we subtract off 4. I always write out what it means to be a square, because this is where people like to FOIL things incorrectly. So we'd get an x squared. Notice we'd get an xh and then another xh. So that's plus 2xh plus h squared minus 4. There aren't any terms for us to combine, and so this is messy, but it's our final answer. And the reason that we looked at x plus h is because we're about to look at some average rates of change, and when we look at that, we can talk about this thing called the difference quotient. And the difference quotient is a key concept in calculus. So if you have to take either Survey of Calculus or Calc 1 at some point in your math career, you'll see this again. So with an average rate of change, we're really looking at a difference of y values over a difference of x values. It's essentially slope, but we usually will have some sort of unit to keep track of. So it might be people per year, or dollars per minute, or something along those lines. So that's where average rate of change can come into play. If you're interested in seeing more, I'd like for you to look at page 188. They talk a lot about average rate of change, but you'll see that it really should just look like finding a slope. The difference quotient is what I want to focus on just a little bit more. So the difference quotient, it's this formula, f evaluated at x plus h minus f of x, f evaluated at x, all over h. So what I thought we would do is we'd look at some examples, and I might only do one right now when we can do more in class. There are also more examples on page 189. So I would like for us to find the difference quotient. This is a formula that I will give you. This is something that I like to ask a question on. Hint, hint, it'll be on your next test. It'll probably even show up on your final. Find the difference quotient for f of x is equal to x squared minus, we'll go with x in this case. So one of the first things I like to do is I like to think about what is f of x plus h. And the idea with f of x is f of x takes its input, it squares it, and then it subtracts off the input. So when we try to evaluate f at x plus h, we take x plus h and square it, and then we subtract off the input, which in this case is x plus h. The parentheses are important. Okay, hopefully you'll think about this as x plus h times x plus h. And then I'm going to distribute the negative, so minus x minus h. We have x squared plus 2xh plus h squared minus x minus h, not x, minus h. That's f of x. If we want to think about what is f of x plus h minus f of x, we're going to take that last line we wrote in red, x squared plus 2xh plus h squared minus x minus h. That entire thing is f of x plus h. And now we want to subtract off f of x, which in this case is x squared minus x. When we do that, we have to distribute this negative. So we're going to distribute the negative sign right here. So let me rewrite this. X squared plus 2xh plus h squared minus x minus h. And when I distribute that negative, I have a minus x squared. And I distribute negative times negative x, that's like adding x. So as we start to look at this, one of the things that we will see is that when we go to combine terms, notice you have a positive x squared and a negative x squared. Here we had a negative x and here we had a positive x. So those terms add to 0 and we are left with terms that only have h in them. 2xh plus h squared minus h. We're almost done now, so we've simplified f of x plus h minus f of x, and we want to actually look at that entire thing as